this lesson, we're going to discuss measures of central tendency. In specific, we're going to talk about the mean, the median, and the mode, and how we can calculate this when we're working with raw data and grouped data respectively. Lastly, we're going to compare the mean against the median, and we're going to discuss when the mean is actually unreliable in comparison to the median. The mean, the median, and the mode, as we said, are measures of central tendency. Now, a measure of central tendency essentially summarizes or describes the data using a single value, and the single value in this case is either going to be the mean, the median, or the mode. Now, the mean is the average of a set of data values. So the way we calculate it is we sum up all of our data values from our data set, and we divide it by the number of data values in that data set. So putting this in a formula, we have x bar. So x bar is what we use to denote the mean, and x bar is equal to the summation of x, where x is the actual data values in our data set, divided by n, and n represents the total number of values in our data set. Now we also get something called the weighted average, and technically you can consider all averages to be weighted. It's just that when we're not given weights, it's assumed that the weight is 1, that the weights are equal, okay? So a weighted average essentially tells us that specific data values have a specific weighting, and we need to take that into consideration. So for example, if you have to consider when you're calculating your final mark, you know that different assessments have different weightings, and you have to take that into consideration before you come up with that final mark. So that's a really good example to consider when you want to understand weighted average, and we will look at that later on. Now, the median is a middle number in the data set. So wherever you locate your median to be, half of the values in that data set will be less than or equal to the median, and the other half will be greater than or equal to that median. So finding the median is a two-step process. Firstly, we're looking for the position, and then we're going to identify the median that's located at that position. So the way we do this is we're going to arrange our data values in ascending order, and we're going to locate the middle position by taking n plus 1 divided by 2. N is the number of data values in our data set. So we're going to take n plus 1 and we're going to divide it by 2 to find the position. So for example, if we had 5 data values in our data set, we would calculate the middle position by saying 5 plus 1 divided by 2, and that would give us 6 divided by 2, which is 3. If you look at the third position, we're going to have 2 data values on either side, because remember we have a data set that consists of 5 data values. So it makes sense to say that that's the middle position, because we have the same number of data values on either side. But what if we had 6 data values? What would our middle point be then? And if you have to think about it, our middle point would have to be positions 3 and 4. Because if we just take position 3 or if we just take position 4, we're going to have an uneven number of values on either side. We're going to have either 3 values less than it and 2 values greater, or we're going to have 2 values less than it and 3 values greater. So in that case, we would actually calculate 2 middle positions. And we do this by taking n divided by 2. So just remembering that same example where we had 6 data points. The first position is the third position, and the second position will be 3 plus 1, which is the fourth position. And to locate the median, it would be the actual value in that position. So we're saying that A is the actual value in position n over 2, and B is the actual value in position n over 2 plus 1. So we would add it and divide it by 2 to get our median. Whereas if we just have one middle position, we would just take the value at n plus 1 over 2. Now, how do we know which formula to use and when we're looking for one position or when we're looking for 2 positions? And it just comes down to whether the number of data values in your data set, so n. If n is odd, you're going to use the first formula to find your position. If n is even, you're going to use the second formula. And it makes sense. When we were working with 5, it was easy to locate a single middle position. However, when we were working with 6, we had 2 middle positions. Moving on to the mode. Now, the mode is a data value that occurs the most in a data set. What we're saying is you're going to go into your data set and you're going to identify the value that's occurring the most frequently. So for example, if in your data set you saw that the number 30 was occurring 3 times and the rest of the values in the data set were only occurring once or twice maybe, then 30 would be our mode because it's the value that's occurring the most. Now it's important to note that they can be no mode. So you can go into your data set and see that every value is occurring the same amount of times, which tells us that there's no mode. Or it's also possible that you can have more than one mode. So you can have more than one value that's occurring the most times, and they all happen to be occurring the same amount of times, right? So if you went into your data set and you saw the numbers 30 and 50 occurring 5 times, and that was the highest frequency or the highest count of a data value occurring in the data set, then we would say our data is bimodal and we would list both of those modes. Okay, so now that we've defined everything, now we're going to move on to working with data. And the first type of data we're going to work with is raw data. Raw data is when you're given the actual data values in a data set. So for example, if we were given this data set that contains temperature values that have been recorded in degrees Celsius, then we would refer to this as raw data because we can clearly see exactly what values are in the data set. So the first question is, what is the average or the mean temperature for the 10 days? So using our formula, where we say x bar is equal to the summation of I equals to 1 all the way up to n of Ti, where Ti is the individual temperatures in our data set, divided by n, and n is 10. So filling in those values, we have 37 plus 39 plus 45 all the way up until 39. We get an average temperature of 38.8 degrees Celsius for the specific 10 days. Next, if we were interested in the median temperature, so the first thing we want to do when we're looking for a median is we want to arrange our data, or we want to sort our data in ascending order. So we're going to sort it from the smallest value to the largest value, right? And having done that, next what we want to do is we want to identify whether the number of data values in our data set, is it even or is it odd? And of course, 10 is even. So we know that we're looking for 2 positions, right? And we're going to use the formula n divided by 2 and n divided by 2 plus 1. So plugging in the number 10, we have 10 divided by 2 giving us the 5th and the 6th position respectively. So in this data set, these are the positions we're looking at, right? And the actual median. Now it's important to note that this is a 2-step process. It's very easy to calculate the positions and then end up calling that your median. First, you're calculating the position and then you're identifying the actual values at those positions, and that's what your median is. So in our case, because we have 2 positions, we're going to sum up the values at those positions. In this case, we happen to have the same value. Now, that's not always going to occur. It's more likely that you're going to have 2 different values. But in this specific case, we have the number 39 occurring in both positions. So, of course, we have a median of 39. Okay, so what I've done now is I've taken that same data set and I've removed a value. So the reason I've done this is because I want to calculate the median, but now if we have an odd number of data values in our data set. So if we had 9 values in our data set, first we want to sort it in ascending order. That's done. Next, we want to identify is 9 odd or even. We know 9 is odd. So we're looking for 1 position and we're going to use the formula n plus 1 divided by 2. So in this specific case, because I've removed that value, n is going to be 9. So we have 9 plus 1 divided by 2 giving us the 5th position. And what is the median? It is the number 39, which is located in the 5th position. So if we had an odd number of data values, this is how we would calculate the median. Okay, so now we're working with that original data again. I just deviated a bit to cover how we would calculate a median when we had an odd number of data values. Now we're working with all 10 data values, and we want to know what is the mode. So remember, the mode is the data value that's occurring the most. So you're going to go ahead and you're going to physically look, and we see that 45 is occurring twice. And 39 is occurring twice, and every other data value is only occurring once. So our modes are 39 and 45, so we have bimodal data. Now let's consider weighted average. So first what we're going to do is we're going to work with abstract data. So it doesn't have any context, we're just going to work with numbers, just to get used to how to plug in the values into the formula. Thereafter, we'll look at a realistic example where we consider calculating the final mark using assessments with different weightings. Okay, so in this table, we have weights and we have data values. So each weight is for a specific data value, right? And essentially the weight is telling us that this data value is going to contribute more to the mean. And this data value is going to contribute less to the mean in comparison to the other weights. So to calculate the weighted mean, x bar is equal to the summation of x multiplied by w, where x is your data value and w is the respective weight that corresponds to that data value. So we would sum 43 times 5 plus 40 times 26 plus 38 times 34 plus 39 times 35. And we would divide this by 5 plus 26 plus 34 plus 5. So writing that all out, we get a weighted average of 39.12. So it's important to note that when you're calculating a regular average where you're not given weights, it is assumed that our weights are 1 or that the weights are equal. So for example, if we were given this data and we weren't given weights, we could still use the same formula, but just plug in the number 1. So we would have x times 1, which is just x. So we'd have the summation of x. And then on the bottom, the summation of our weights would be 1 plus 1 plus 1 plus 1, which is 4, which is the number of data values. So you can see how this formula would collapse back to that formula we were using previously. All right, so now we're putting that concept into a realistic scenario, and this would probably be useful for you when you want to calculate your final mark. So we are told that for maths, the final mark is calculated using these 4 assessments, where test 1 and test 2 contribute 15%, the assignment contributes 20%, and the exam is contributing 50% to the final mark. So we can see that these weights that have been given will sum to 1 or 100%. So that's not always the case. Your weights don't have to sum to 1, but of course in this case, we expect it to sum to 1 because we know the final mark is 100%. And we're told that John obtains these grades. So there's a student John and he gets 70% for test 1, 62% for test 2, 90% for the assignment, and 72% for the exam. And we want to calculate John's final mark. So the way we're going to do this is we're going to use a weighted average. If these assessments were all contributing a quarter, so 25%, then we could go ahead and just use the original formula because they're equally weighted. However, we can see that these assessments have different weightings. The assignment contributes more than the tests, and the exam contributes more than the assignment and the tests. So what we want to do is we want to use that weighted average formula where X is going to be the grades that John achieved and W is going to be the weights for each assessment. So plugging in those values, we have 0.7 times 0.15 plus 0.62 times 0.15 plus 0.9 times 0.2 plus 0.72 times 5. And the bottom, as we expect, is going to sum to 1. So you could have just gone ahead and put a 1 there as well. And this tells us that we get a weighted average of 0.738. So we have a weighted average of 73.8% or a final mark of 73.8%. Now let's discuss grouped data. So when we're working with grouped data, that essentially means we've been given a frequency distribution. So if you don't know what a frequency distribution is or how to come up with it and you want to know, I have covered previous videos where we discuss this. Essentially, this is what a frequency distribution looks like, not including this last column, right? So I've added on this last column, but a regular frequency distribution will have your class boundaries and your frequency, and it may have midpoints. So this frequency distribution was actually constructed from the temperature data. So when we were working with raw data, it's that exact same data that we were working with previously that I've converted into a frequency distribution. So our boundaries, these are our class boundaries, and the frequencies are telling us how many data values lie in these boundaries, where we read these boundaries as greater than and equal to the lower boundary, but less than the upper boundary. So if we had a value 31.5 in our data set, we would say that it lies in this class boundary because 31.5 is not included in the first class boundary because it's an upper bound there. Then the midpoints, the way we calculate the midpoints is by taking the lower boundary plus the upper boundary divided by 2. So we do that for each individual class boundary and we get midpoints. Then this column that I've specifically added it because we need it for what we're about to do. And what we're doing here is we're taking the frequency multiplied by the midpoint to get this answer. You can see 1 times 29.5 is 29.5, 4 times 37.5 is 150, 2 times 45.5 is 91, and then I've summed them all up to get a total of 387. So in this lesson, we're discussing the mean, the median, and the mode. However, we're only going to calculate the mean for grouped data. Is it possible to calculate the mode and the median? Yes, it is, but we're not going to discuss that in this lesson. There's many ways that you can come up with the mean. However, we're going to focus on one specific formula. So if we were interested in the average temperature, we're going to use this formula where we sum up the frequency multiplied by the midpoints and we divide it by n, which is our total. So that is why I went ahead and created this column. Sometimes it's easier to write it out in the table itself and then just plug in the value afterwards. So you can see that the summation of the frequency times the midpoint is given by this value of 387 divided by 10, our total, which gives us an average temperature of 38.7 degrees Celsius. So if you think back to when we worked with the raw data, we actually got an average of 38.8 degrees Celsius. So of course we're not expecting the same value because we're not working with the actual data values. Now let's compare the mean and the median. So the mean is actually the most reliable when our data is symmetric or bell-shaped. So when we say that we have symmetric or bell-shaped data, that means that we have no outliers present. What is an outlier? An outlier is an extreme value. So it's either a really high value or a really low value in comparison to the rest of the data values in the data set. So for example, if we had a data set with the values 10, 20, 30, 500, 850, we can clearly see that the values 500 and 850 are very large compared to the rest of the data values. And this suggests to us that these are outliers. Okay, so this is what a bell shape or symmetric data set would look like. You can see it's appropriately named because it's the shape of a bell. And we say symmetric because if you had to draw a line down the middle, it looks like a mirror image on either side. So for bell-shaped data, our mean would lie somewhere down the middle. And we say that for bell-shaped data, the mean is most reliable. If we had a data set where we had a handful of really high values occurring, it would cause the shape to now pull to the right. Okay? And we would refer to that as positively skewed data. So as you can see, this was the original shape, but because we had these really high values occurring, it caused the data to pull to the right. So if we wanted to put this into context, let's assume that in a class, most of the students scored 60% on a test. However, there were a handful of students that scored 90% and above on that test. So what would happen is, because of those students who have such a high grade, it would cause the mean to be high. Because remember, how do we calculate the mean? We sum up those actual values and we divide it by the total number in the data set. So where the mean was originally around here, because of those extreme values, we're going to end up with a higher mean that's probably around here. And this is not reliable because let's assume that when we calculated the mean, we got a mean of about 80%. Now that is mathematically correct. However, it's not giving us accurate information because it's telling us on average, students scored 80% in this test. But that's not true because we know that most of the students scored 60%. So saying on average that students scored 80% isn't an accurate representation because this 80% is only because of those students who had such a high mark. Of course, we could have the opposite occurring where we have some really low values in the data set, and it's the same concept. So when we have outliers present, we say that the median is more useful because the median is not affected by extreme values. If you think about how we calculate our median, if we have 11 values, then our median is located at position 6. Okay, and regardless of whether we have outliers in that data set or not, the median will always be located at position 6 for a data set with 11 values. So because it's not affected by extreme values, we say it's more reliable. If we wanted to consider the example we were looking at previously, let's say there are 11 students in this class. 4 students have a grade of 90% and above, and 7 students scored around 60%. If we were to identify the median, we would look at the 6th position and we would get a median around 60%, of course, because 7 students, remember we put it in ascending order, 7 students got around 60% and only 4 students got a mark of 90% and above. So we would get a median that's around 60%, and that's more reliable when we think about the actual data in comparison to getting a mean of 80%, which doesn't necessarily make sense when we consider the actual data. That brings us to the end of the lesson. Thank you so much for watching. If this video has helped you in any way, kindly like and subscribe and turn on that notification bell to keep learning.